potentially have to learn how to cover that. So the topic that I'd like to share with you today is a method we do in encapsulation of gas sensors to operate in the gastric continuous monitoring. I will give you the motivation why are we interested in this. So continuous monitoring of vital signs has been common practice in the intensive care unit setting. And however, so the other different kind of biomarkers like inflammatory biomarker or like gaseous biomarker, the only way you can detect it or what to apply this information is through blood testing. So although this blood testing is universal, and however, it is a notorious painful invasive procedure, and it is also a time-consuming process. Maybe another feasible solution for continuous monitoring. From our observation in clinical studies, we found out nasogastric tube is commonly employed in the ICU setting, and we use it for continuous harvest in the gastric point for analyzing some of the interesting biomarkers and also delivering. Then here comes the question we start to ask ourselves: is it possible for us to detect some of the biomarkers we are interested in blood serum? And can we find a correlation between? In order to answer this question, my colleague and I, is currently bio, and we start to look into different kinds of biomarkers we can find in the human body. We start to look into 154 different kinds of biomarkers, and among them, we found it is actually very interesting. There are around 146 biomarkers we can find in gastric fluid, and also in the blood serum, we found there's about 125 biomarkers we can find in blood serum. That means there's overlapping between around 94% overlapping that the biomarker we can find in blood serum, we can also find in gastric fluid. So we start to ask another question for ourselves: will it be possible to integrate a sensor directly onto the nasogastric tube? We can enable continuous monitoring. Then in order to do that, we start to do a proof of concept study. In this in vivo study we try to use a large animal model, which is the pig, and then we try to leverage the ketoacidosis as our disease model. We use we try to intravenously inject ketone body directly into the animal in order to stimulate ketoacidosis. Then we try to understand, is it possible for us to measure the ketone body directly in the gastric fluid through a gas sensor? This gas sensor is a off-the-shelf sensor. SGB40 we purchased from Sensorion, and then BME 680 is the sensor from Bosch. And we try to integrate everything together, and then we start to do the in vivo study. Here you can see when we, as a reference glucose information here, we collect the blood to do a blood testing. When we inject the ketone body into the blood vessel of the pig, and then you can see the blood reflect the increase of the ketone body, and also in the gastric fluid also increase in the signal. And in our sensor also correspondingly respond to the variation, to the increase of the ketone body. Then, based on this successful study, we also start to look into using the same sensor and then to see the response of isoflurane, which we commonly use in useful anesthesia. And we can see when we deploy this sensor through the ladle and then into the gastric environment, this temperature increase from room temperature to the body temperature. And then when we slightly increase the isoflurane concentration about 1%, we can see the sensor can also accurately capture this increase of the isoflurane. But you can see in the time scale here, for this sensor, we are very limited to a very short window, around less than 2 hours. This is because the primary encapsulation method we used before cannot make the gas sensor to survive in the gastric environment for long-term period. And so here comes the challenge. When we are trying to use a gas sensor to operate in a gastric environment, basically similar to gas sensors into gastric fluid. What kind of challenge we need to solve, we need to address? First of all is the chemical corrosion, because the gastric environment is actually a highly acidic environment, will make the chemical corrosion very severe. And also mechanical corruption is another issue, because the nasogastric fluid need to experience very strong mechanical contraction from the stomach, because the stomach is designed to smash the food, and also the interaction with the food will create reflection on the membrane to damage the sensor performance. And also electrical shocking is a very important issue, because the environment is highly humidified environment, and because we cannot do a complete shielding of our sensors from the environment, if we do so, the gas permeability will be extremely low, then we will not have the chance to detect the volatile organic compound using the gas sensor. So in order to make a kind of gas sensor to survive in the gastric environment for long term, we have to solve all of this problem altogether. In order to do it, we propose a new kind of conformal coating method for the metal oxide gas sensor. Here you can see we actually have 3 different protections of the coating on the sensor. So here, this is the sensor, the SGP40 from Selsing. On top of the sensor, it actually has come with an intrinsic membrane. So we use SEM to analyze this membrane. You can see this membrane is highly porous in order to allow the gas to transport in. And this membrane is also very important to shield the airflow noise onto the metal oxide sensor. On top of the sensor membrane, we do conformal coating of parylene type C. Coating here, you can see it's a very dense polymer coating here, and which gives us a much lower moisture permeability to protect electrical shorting and also chemical corrosion protection. On top of the parylene coating, we do PCR coating. Here, the PCR coating is slightly different to the conformal coating method people used before. We actually we dissolve PCR into a BCM solution to, by evaporating the BCM solvent, we can create this kind of highly porous structure. This is particularly important because we need the PCR to be thick enough to protect the parylene coating, because parylene is actually much brittle than all the other coatings. The mechanical corruption will actually damage the parylene coating. If we don't protect parylene coating by PCR, then the sensor will again have to survive for long term in the gastric environment. So we need a very thick PCR. At the same time, we hope this PCR coating will not affect the gas permeability into our sensor. So this is very important to protect for the mechanical corruption that also give a high gas permeability. So with this coating method, we can start to do the evaluation of our sensor. So here, in order to do the long-term evaluation of this sensor, we developed a setup to simulate the gastric environment. So here we have our electrical diagram of our system setup. We have 8 identical sensors connecting to a multiplexer and interact with a single microcontroller here. And then we have a second microcontroller used to control 3 different pumps. And the 3 different pumps will allow us to emulate the gastric environment. The first pump enables us to feed in fresh stimulated gastric fluid. The second pump will add the volatile organic compound on the left side into the solution. And the third pump allows us to completely empty the gastric environment. And here is the setup. You can see there are 3 tubes connecting to the 3 pumps. And then we have the gas sensor and it's submerged into the simulated gastric environment. We have a hot plate. The thermocouple control the entire environment temperature to be 50 degrees. And more importantly, we need to use a silicone cap to cover everything here to maintain the entire environment to have 100% humidity to reflect the real gastric environment. So before we look into the long-term performance, we need to prove the porous PCL conformal coating actually do not affect the gas, the dynamic response of our gas sensor. So in order to start it, we prepared two identical HPV40 sensor, one with the 100 micron PCR coating, the other one is without coating. So here you can see for both of them, they can respond to the presence of the VOC vapor almost immediately. And however, the PCR coated one shows much less noise due to the temperature perturbation or any kind of flow perturbation in the air. And when it comes to when we take the sensor out from the VOC vapor, we can see the coated sensor actually recover much slower than the coated one. Our hypothesis here is there are probably some of the VOC sensor being trapped in the porous structure of the PCL, which make the recovery time much longer than the coated one. But we actually much focus on much interested in the sensor response, but when there's a presence of the VOC vapor. And then once we prove the PCL actually works well, then we start to look into the perylene coating. And the perylene coating plus the PCL coating can enable for the long-term performance. And also, if the entire sensor still responds, still sensitive to the VOC signal. And we start to look into the HPV40 sensor with two different coating thickness, the perylene coating thickness. And as we know, if you have higher thickness of the perylene coating, you actually will reduce the sensitivity of the sensor. So here we study the dynamic response of the sensor when we have the HPV40 sensor and BME688 sensor together submerged into the stimulated gastric fluid, and then we add VOC as the step one. And here you can see with the 10 micron coating, the sensor responds almost immediately, and then slowly reach to a steady state. In the step two, we start to refresh the gastric environment, and then here you can see from the temperature reading, the system starts to have the temperature perturbation. This is because when we refresh the solution, it's actually using the tap water with the room temperature. And then when we completely empty the environment, the sensor will slowly recover to the original value. And when we increase the thickness to 20 microns, then we can see the response. The sensitivity is actually much lower than the 10 micron coating. And then it's also much more sensitive to the temperature perturbation. Here you can see the BAC688 temperature perturbation, and then the HPV40 is also responding to this temperature perturbation. And we also did the standard variation characterization of our sensor. So within identical sensors, we can get the variation less than 2% in the 10 micron coating, and then around 2% in the 20 micron coating. Between sensors, we can get the variation less than around 5%. And then, so we all know there's a strong trade-off between the sensor lifetime and the sensor sensitivity. Then here we compare these two types of sensors with different coating thickness. We can see deeper coating can significantly improve the sensor lifetime. And then, of course, the sensitivity and response time will take much longer if you have the thicker coating. So as a conclusion here, I want to share with you we successfully enable the gas sensor to operate in the stimulated gastric environment with a sustained performance. And but we can also see the sensor respond almost instantly to the presence of VOC, but it will recover very slowly when we remove the VOC. So the next step will be consider how we can accelerate the recovery of the sensor. And the major challenge here would be if there's a larger temperature variation, this will induce the condensation inside the gas sensor, and this condensation will significantly attenuate our long-term performance of the sensor. This is also the main reason why the sensor lifetime is limited to less than 2 weeks. If if we are able to address this condensation issue, the lifetime can be much longer, and also the deviation will be much smaller. And our future work will focus on to implement the long-term study in vivo on our